All right, today we're talking about related rates. This is another concept that is not going to be a lot of learning new things. We're not going to be learning how to take derivatives again. We're not going to be learning any new techniques for that. What we're going to be learning is how to solve some word problems, which y'all know how much fun that is. But we're going to be talking about solving some word problems today. And as I said, the title is Related Rates. Now I have a question. What is this a picture of? A bicycle. Very good, okay. Have another question for you. How do you make the bicycle go?
Pedals.
The pedals, okay. So when you press on the pedals here, it turns this thing. Anybody know what that's called?
Chain.
The chain, but the thing that the chain turns on is called a sprocket.
Yes.
And then it makes this sprocket back here turn, which turns the wheel, which makes the thing go, right? All right, one more question. Why aren't the sprockets the same size?
To help the transfer of energy.
One
To help the transfer.
makes it turn faster.
One makes it turn faster. What do you mean?
Because one's bigger than the other.
So the fact that this one's bigger makes what turn faster?
The smaller sprocket.
Okay, so you're telling me if I turn one complete revolution here, what's going to happen back there?
It's gonna make two.
It's going to make more than one, right? One revolution here is more than one revolution back there, right?
Yeah.
Does everybody agree with that? Okay, because if you have, how many of you have a bicycle? How many of you have a 10-speed bicycle or maybe faster or something like that? How do they make bicycles have different speeds?
Different size sprockets.
They put different size sprockets back here and you change the gears, and if you go to a smaller sprocket, two things happen. What happens?
It's easy.
It goes faster, and if it's back here, if the one smaller is back here, it's harder to pedal, isn't it? Or is it easier to pedal? I don't remember.
The smaller, easier.
Smaller back here makes it easier to pedal. Okay.
Because they get, like,
Because
as
it's
it gets
smaller.
more-
That's right, because it's turning it faster.
As
Okay.
it gets like the same size as the large sprocket, it gets
Right.
harder.
Be harder and harder. So that's what happens with it. But the smaller we go back here on the backside, the faster the bicycle goes. So this is an example of related rates. Okay? Every time this turns one revolution, every time the main sprocket turns one revolution, this back here turns, but it's not necessarily one-to-one. Do you understand what I mean? This one turning once doesn't mean this one back here turns once. Agreed? Let's look at a couple of other examples if I can find them here. Related rate problems. Okay. This is off somebody's college website, and I want to look at a couple of these. Let's look at this one here. That's what I want. Okay. Now, just while I'm talking, look at this. This is a cone. Okay. The red is the actual cone, and the blue, think of that as water being poured into the cone. Okay. So we've got a cone here. So it's small at the bottom, big at the top, and we're just pouring water into the top. Look at what's changing as we pour water in there.
The rate at which it fills.
The triangle is changing, but the rate at which it fills, I don't think the rate is necessary. It could be changing, but let's assume that we're constantly pouring in at the same amount. What's happening though? As we pour water in,
More space in the cone.
it's filling up more space. But notice what happens the further up I get. What happens to
There's
the...
more space, so it
slower
takes more time.
The slower it looks like it fills up. Would you agree with that? Down here, it looks like at the bottom, it looks like it's filling up really fast. But then the closer you get to the top, it's filling up more slowly. Now, we're pouring water in at the same speed all the time. So the rate of the water coming in is the same, but how fast it's spreading out is slowing down. Yes, sir. I am recording. Thank you for asking, though. So, do you understand? This is another example of related rates. The water's going in at a constant speed, but the height is not changing at the same speed. The radius or the diameter of the water is not changing at the same speed. Okay? Let's see if we can find one more example. just so you've got a pretty decent picture of what's going on here. Not the fish. I want to. There we go. That's actually not the one I want to see. Hold on. I want to find the football. Where's the football? That one would work, but let's do this. This is a. I did not ask to do that. I asked to do that. Okay. Now, look at this circle here. It's growing. Would you agree with that? As the circle gets bigger, doesn't the radius have to get bigger?
Yes.
All right, now I've got a question for you. Is the radius getting bigger at the same speed as the area is?
No.
Because when the radius gets twice as long, the area has gotten much bigger. So the rate of the radius, the red line, the rate of it getting bigger is different than the rate of the whole area of the circle. Agreed? But they are related to one another, aren't they? If you can figure out something about one, you probably know something about the other. So that's what we're dealing with related rates. Anytime we're dealing with related rates, we're dealing with two things we can measure that are both changing with respect to time, is the basics of it here. Everything is changing with respect to time. Now, it could be with respect to something else, but that's above our pay grade. Everything we deal with related rates, we're talking about changing with respect to time. Okay? Changing over time. Now, what does change make you think of? Derivative. So we're looking at a derivative if we're talking about change, derivative, change over time. So we're looking for a derivative of something with respect to t. So you'll be taking the derivative of the radius with respect to time, the derivative of the area with respect to time, the derivative of the position with respect to time. That's what you'll always be looking for. So all of our derivatives are going to be implicit differentiation that we deal with, okay? All of it will have everything will be a derivative with respect to time as we deal with it. Okay? There are a few just basic problems that we're going to work through, and that's our goal today. We're going to work through 6 or 7 problems. I strongly encourage you to stay with me and try to understand what's going on here. We're going to start off with some that are not word problems. This is just a math equation. What do we need to do with this? Okay, so let's look at this. Suppose x and y are both differentiable functions of t. That means we can take the derivative with respect to t, and that they're related by y equals x squared plus 3. This says find dy dt when x is 1, given that dx dt is 2 when x is 1. Now all of that just kind of scares you to begin with, right? Okay, now let's forget about the scariness of it here, okay? We've got an equation here, y equals x squared plus 3. Let's write down what we know here. We know that x equals 1. We know dx over dt equals 2. And we're trying to find dy over dt. Would you agree with that? That's in a synopsis what we've done there, right? Well, how do you think we ought to do that? Well, we've got a dx dt. We've got an x over there, don't we? But we don't have a dx. Is there any way to get a dx dt in here and a dy dt? Take the derivative, okay? So if we take the derivative of this, we get dy dt equals, what's the derivative of x squared? 2x dx dt. What's the derivative of 3? 0. Okay? Now, we wanted dy dt. We've got that dy dt is 2x dx dt. So what do we need to do? We can put in what for x? 1. 2, 1. For dx dt, we can put in 2. So then we know that dy dt equals 4. This is very important to note when x equals 1. Okay? is what is dy dt when x is 2?
6.
Be a 2, we'd replace this 1 with a 2, wouldn't we? So it'd be 2 times 2 times 2 would be 8. So do you see that dy dt is changing all the time? Okay? Do you understand that a little bit? That's just brute force algebra. Once you take the derivative, it's just algebra after that, isn't it? And I think that's what you're going to find. We're going to have to take derivatives and then do a bunch of algebra to it, okay? Any questions about that problem so far? All right, let's look at the next one. A pebble is dropped into a calm pool, causing ripples in the form of concentric circles. The radius of the outer circle is increasing at a constant rate of 0.75 feet per second. When the radius is 5, at what rate is the total area of the water changing? Okay? So has everybody got a clear picture of what's happening? Lake's smooth, nothing's happening to it. And you drop a pebble into the middle of it, and what starts happening? It's going to start rippling out, okay? So what are we told here? We're told that the radius is increasing at 0.75 feet per second. Okay? What is that? Is that an R? Is that an A? Is that an X? Is that a Q? What on earth? How can we describe that?
Feet per second for acceleration, rate.
Feet per second is our units. And to me, that is a dead giveaway for what it is, okay? Feet per second. That's a rate. The bottom is measured in seconds. Seconds is the same as time, right? So that's a rate of something with respect to t. It's a rate of what? The radius of the outer circle is increasing. The radius is increasing. So this tells us that dr dt is 0.75 feet per second. Let's write that so we can actually read it. dr dt is 0.75 feet per second. Okay? That means for every second the radius is getting 0.75 feet longer. It's getting 9 inches longer every second. In 2 seconds it's 18 inches longer. Keep going, okay?
You download the Notability update?
I did.
Pretty useful.
When the radius is 5 feet, what does that tell us? R equals 5, right? When the radius is 5 feet, at what rate is the total area of the water changing? What is that asking for? Rate of area. At what rate is the area changing? So what does that tell us? We're looking for derivative. Derivative of what? Rate is the total what? Area. So we're looking for a derivative of area. We're looking for the derivative of area with respect to time. Now, what's missing in this problem that was in the other problem?
Numbers and stuff. An equation.
An equation. We've got numbers just like we did before, but we don't have an equation written down. But you know an equation, don't you? What equation are we going to use, Miranda?
Pi r squared.
What equals pi r squared? Area equals pi r squared. Now, how did she come up with that equation? Area of a circle. We know we're dealing with circles. We know we're dealing with area, so area equals pi r squared. Now, what do we need to do with that? Take the derivative. The derivative of area is dA over dt equals, what's the derivative of pi? How are we going to do that pi r squared? Product rule? 2 pi r. Why don't we have to worry about the derivative of pi? Why don't I have to do a product rule here? It's a constant number. 2 pi r dr dt. It's important to put that dr dt there. Why is it important to put the dr dt there? We're taking the derivative with respect to time. We aren't talking about the derivative with respect to r. We're talking about the derivative with respect to time. Because the radius is changing as time goes on, the area is changing as time goes on. Yes, sir?
We have something for DRDT.
We have something for dRdt, and we have something for r. Okay? So we're going to get 2 pi times 5 times 0.75, which works out to be 7.5 pi. Now, please understand, that is not the area of the circle. It's the rate at which the area is changing. This is feet squared per second. The area is changing at 7.5 pi feet squared per second at that instant. What about when the radius is 6? Will dA dt be the same thing?
No.
Will dr dt be the same thing?
No.
Why not?
Because it's expanding.
Okay, let's go back and look. A pebble is dropped into a calm pool causing ripples in the form of concentric circles. The radius of the circle is increasing at a constant rate. What does that mean?
It keeps going.
It keeps going at that same rate all the time. So dr dt is always 0.75 for this scenario that we're dealing with. You've got to be careful and read that, okay? Sometimes it's only 0.75 for that specific instant in time. But in ours, it's always 0.75. Question for you. Why did we put positive 0.75 and not negative 0.75?
Because it can't go back. It can't expand inward. Yeah.
It can't expand inward, okay? What words up here tell us?
Increasing.
Increasing, okay? If it had said decreasing, we would have scratched our head and said, how is this happening? But we would also know that it has to be negative 0.75, okay? So that all of those are little nuances you've got to be sure and be careful of as you work through this. So we found out that dA dt is 7.5 pi feet squared per second. How did I know it was feet squared per second? It's area, but why isn't it miles squared per hour?
Because it's feet. If it was going miles.
Because our original thing was feet per second.
What's 5 measured in?
Feet per second.
Feet.
Yeah, that's expanding.
And this was measured in feet per second. So when I multiply feet times feet, I get feet squared. Okay? That's just a good thing. The reason I'm writing that out is I think that's a very good way for you to check your answer. To be sure that you're going, if you've got seconds there and feet per second there, you're not going to get feet squared per second over here. So be sure your units match up with what you want in the end. All right, let's look at another problem. Air is being pumped into a spherical balloon at a rate of 3.875 cubic feet per minute. Find the rate of change of the radius when the radius is 3 feet. Okay? Somebody tell me something we know.
We have a rate.
We have a rate. We have 3.875 cubic feet per minute. Well, what is that? That's the rate of what?
The volume when you're pumping it.
The volume.
The volume of the balloon. This is dV over dt. Now, tell me some ways you know that it's the volume.
Cubic feet.
Cubic, we measure volume in, okay? Anything else that tells you it's volume? Air is being pumped into a spherical balloon. So air is going in. Think about what's happening when air goes into something.
It pushes out.
It gets bigger. It blows up, okay? So we've got dV dt. All right, tell me something else.
The R equals 3.
R equals 3 because the radius is 3 feet. Okay? Anything else? Well, what are we looking for? So what is that? The rate of change of the radius.
Fast it's going like it's not flat.
Yeah, so what are we going to write down for that though?
The
All right. We want the rate of change of the radius. What is that? What letter are we going to use to stand for that? Rate of change of the radius. What do you think we should use? dr, but dr's got to be over something. dr dt. So we're looking for dr dt. Now, we need an equation. What kind of equation can you come up with? How do you decide what your equation needs to be might be a better question.
Based on the shape.
Based on the shape, but not always are we going to have a shape. But I mean, most of the times you can draw a picture of it. Look at what you're given here. I've got dv dt, dr dt, and an r. Do I have any equation in my mind that deals with v's and r's when we're talking about a spherical balloon? Can you think of anything?
4/3 pi r cubed.
Volume is 4/3 pi r cubed.
Is it right?
Yes, that's right. That's right. The volume of a sphere is 4/3 pi r cubed. I just pulled that out of the air because I remember it. You need to be able to remember that as well. If you don't, it's probably on one of the cheat sheets that I gave you somewhere. So we have an equation. We've got all this stuff over here. Tell me what we need to do now. Take the derivative. dv over dt equals. Now this 4/3 pi is all just stuff. So I'm going to write it down. Which winds up being what? 4 pi r squared dr over dt. Okay? Now, plug in what we got. Where does the 3.875 go? dv dt. Now, that's different than what we've been doing. In the past, we've been plugging it in right over here for dr dt. But remember, this is a volume change the dv dt is. So it's 3.875 equals 4 pi. What are we going to put in for r? 3 squared dr over dt. Now it's a calculator problem. Yes, you should use your calculator to figure out what that is. I'm just going to write it down. dr over dt is 3.875 over 36 pi. And you're smart enough to figure out what that answer is. I don't know what it is. Is that simple enough? What would our answer be and what would be the units here?
Feet to the fourth.
All right, we're measuring dr. What do we measure r in?
Feet. Just
Feet
I'm sorry.
per what? Feet per minute. That would be our units that we should get there. Remember when you're dividing that on your calculator that the 36 pi has to be in parentheses because you want to multiply them first and then divide. So that's going to be a really small number. I don't know what it is, but y'all are smart enough to figure that out. Any complications there so far?
Drew, what'd you get?
0.0334.
No, 338.
338, okay. 0.338 feet per minute. Okay? Does that sound logical? That the radius is going to be increasing but not at a really big place? Because think about it, you've been blowing on this balloon for 5 seconds. What's happening? What happens when you blow on a balloon? It blows up quick, and then every breath makes it get a little bit bigger, but not a lot bigger, right? Because you got all that area to move around in there. So you expect it to be smaller. If we did this for r equals 5, what would we expect to happen? Would this be a larger number or a smaller number? When r is 5. Think about it. Radius is 3. As it gets bigger and bigger, what happens? Real life, what happens? The more I blow on it, is it keep getting bigger? Yes, but it's getting bigger at a slower rate. So yes, we'd expect it to be a smaller number there. Okay. How do y'all like this so far? Is it complicated yet?
It's not too bad.
All right. An airplane is flying at a constant altitude on a flight path that will take it directly over a radar tracking station. If the distance between the plane and the tracking station is decreasing at a rate of 300 miles per hour, when the distance between them is 13 miles, what is the speed of the plane? Wow. Give us all that information and not even a picture, so that sounds very hard, doesn't it? Well, let's see if we can start drawing a picture of it, okay? Let's see. When an airplane. All right. There's our airplane, okay? Airplane is flying at a constant altitude. What's altitude? Height. So that's saying that this h is constant. So that tells you something else too. If h is constant, what else does that tell you? Derivative is constant. H is constant, therefore dh dt equals 0. Agreed? Because it's not going to be changing. And it's going to take it directly over a radar tracking station. Now let's see. We'll call this building here our radar tracking station. And it has some kind of something like that on it. How do I make this thing look like it's maybe something like this? I don't know. It looked better, didn't it, to begin with? And there's our radar tracking station, okay? There's the radar on it. It's tracking it. Okay? If the distance between the plane and the tracking station is decreasing at a rate of 300 miles per hour. Okay, let's break that down and draw it on our picture here. The distance between the plane and the tracking station. What's the distance between the plane and the tracking station? How do I measure it? Where would that be up here, you think? Be in miles, but somebody want to come draw it up here or point it out to us or describe to me where you think it is?
Bottom axis.
Okay, that's my question here. Is this what it is?
Oh, no. Oh, it's the slope.
You think it's that? Which one is it? Is it the green line or the red line? Because that's the real crux of the matter here. If the distance between the plane and the tracking station. Now, where's the plane? Okay, it's here. The tracking station's at the bottom. If I tell you to measure the distance from here to somewhere, aren't you going to go straight to that somewhere? Not straight underneath it. If I said to straight underneath it, or if I said to where it is directly above the ground, I think it'd be talking about the green line. So I think we're talking about the red line here, okay? The distance between the plane and the tracking station is decreasing at a rate of 300 miles per hour. So what does that tell me? What do y'all want to call this red line? Let's give it a letter. That's H, so what do we want to call this maybe? X, okay? So what does this tell us right here? What does that tell us about X? The distance between the plane and the tracking station is decreasing at a rate.
Negative 300.
Negative 300. What is negative 300? Is X negative 300?
R.
It's
dx dt is negative 300. Okay? dx dt is negative 300. Okay? Is everybody comfortable with that now? Because that's confusing to us here. All right? Is decreasing at a rate of negative 300 miles per hour when the distance between them is 13 miles. So what's 13 miles? X is 13 miles, okay? Because that's the distance between them. What is the speed of the plane? What is that asking for? How fast the plane's going.
I said 200.
Okay. How fast is the plane going? So let's see if we can The plane is moving this direction, right? Can we just use this green line down here to represent the plane moving? Because, I mean, it's the same thing. It's just, I've just moved it down here, right? Let's call this y down here. So we're asked to find what dy over dt is, right? What is the speed of the plane? That's what we're asked to find. Is everybody comfortable with that so far? Okay. So, what are we going to do now? We need an equation that relates a bunch of these letters we've got up here, don't we? Anybody know of an equation that
X squared plus y squared equals to 160. I think h squared plus y squared equals x squared.
all right, I get h squared plus y squared equals x squared, and you were saying x squared plus y squared equals what?
Just the 13 squared.
All right, you're saying x squared plus y squared equals 13 squared? But x is 13.
So it's the same.
Okay. All right, what y'all think? We got two equations here. Which one do you think looks better? H squared plus y squared equals x squared, or x squared plus y squared equals 13 squared?
H squared plus y squared.
This is a Pythagorean theorem, isn't it?
Yes.
So I think it's going to make us a little more sense. I think that's going to be easier to deal with. X squared plus y squared is just...
H. I said it's h.
Okay, okay. All right. So you said the same thing as that there. Okay. All right, okay. I'm with you now. So let's see. Well, what can we do with this thing here then? H squared plus y squared equals x squared. What do you think we need to do now? Take the derivative, okay? So 2h...
If we know what x is,
Would you agree with that? 2h du h dt plus 2y dy dt equals 2x dx dt. Well, what do you want to do now? Let's plug in some numbers, okay? Well, talk to me about, first of all, anybody have a problem with me throwing away all the 2's? Because if I divide everybody by 2, they're going away. To me, that just cleans things up, okay? So we can throw all the 2's away. We can just cancel them out. Boom, boom, boom. Now, what is dH dt?
0.
0. So this is immaterial, right? So we can say this whole thing up here is 0. So now look at what we've gotten down to. We're at y dy dt equals x dx dt. Right? Well, what can we plug in? We've got a 13 and a negative 300, don't we? So we can say y dy over dt equals, what's that, 13 and negative 300? So dy over dt is negative 3900 over y. Would you agree with that? Anybody see a way to figure out what y is? Yes, sir.
Oh, never. Well, no, never mind. I was going to say we could plug it into our Pythagorean theorem down there, but we would need something for h.
We would need something for h, and we don't have anything for h, right? Okay? So does everybody agree, if we had something for h, because that's the observation I wanted you to see, if we knew that he was flying at a constant height of 5 miles, let's do that. 5 miles. Okay? We're changing the problem on the fly. So he's flying at a height of 5 miles. How does that help us now?
Y equals 12.
Now we can figure out what y is, can't we?
5 squared plus y squared equals 13.
Right. So now we can say 5 squared plus y squared equals 13 squared and find out that y is 12.
Pythagorean triples.
Yep. So then we get dy over dt equals negative 3,900 over 12, which is negative 300 and something, right? 36, negative 330, no, negative 325, I think. 12 will go into that 36, give you 3, 30, it'll go 2, 24. Okay, negative 325. So he's flying at negative 325 miles per hour. What does the negative mean? He's going backwards?
He's descending.
No, we just said he's flying.
No. He's approaching the, what you call it.
He's getting closer to the radar station, okay?
Yes.
So that means he's getting closer to the radar station all this time, okay? That's the reason it's negative 325. Now what about when he gets closer in? When y gets closer, well, let's don't go there,
He's
okay?
going faster.
He's going to be going faster then, or he's going to look like he's going faster then. Does that make sense?
Yeah, it's like the closer you are to a car, the faster it looks like it's going.
Do y'all agree with that? You know, if you're watching something way off, he doesn't look like he's going fast, but the closer he gets, the faster he looks like he's going. So that's what we're saying there. Yes, sir. Yes, you may. Okay. A camera is stationed 2,000 feet from a rocket that is being launched into space. The rocket's position at any time can be found by the equation S equals 55t squared. Find the rate of change of the angle of elevation at 12 seconds after liftoff. Wow. What do you think there? Can you draw a picture of that? A camera 2,000 feet away from a rocket. Okay. Whoops. Okay, there's our rocket. Sitting on the ground. All right. And our camera is 2,000 feet away. So here's our camera over here, okay? Does that look like a camera maybe? Not really, does it? And this distance is 2,000 feet. What letter would you want to use for calling that distance there? X, okay? If that's x, then talk to me about dx over dt.
It's
100 dx dt is 100 dx dt is 110t. Why do you say that?
because the S equals 55t squared.
This is s, but we're talking x down here.
S is the rocket. Oh, never mind.
You're asleep. Somebody talk to me about what dx dt is here, okay? Come on now, you're smart people. Huh? 2,000? So the rate of change of x is 2,000.
0.
0. Why 0? Why 2,000? The derivative of 2,000 is 0. I agree with that. But over here, when x was 13, the derivative of 13 wasn't 0. So why is it 0? 0 is the correct answer over here. My question to you is why? What's not moving? The rocket, okay? The rocket's not moving, but more importantly, the camera's not moving, is it? No. This distance is measuring from where the camera is to where the rocket is seated right now. Now, nowhere in here does it say the camera's moving. So we assume that when this rocket, I wonder if I can do that. I can't do that. Well, I can't do that. Okay. We assume that when this rocket gets on up here a little ways, that what? The camera's still there. This distance from here to here is going to stay the same. So dx dt is 0. Nowhere is that written in the problem. You've got to figure that out on your own. Since that distance isn't changing, dx dt equals 0. Okay? The rocket's position at any time can be found by the equation s equals 55t squared. All right, big deal. Find the rate of change of the angle of elevation. The rate of change of the angle of elevation. What on earth is the angle of elevation?
When the rocket goes up, you have to tilt the camera.
Very good. If I'm sitting here, when that rocket's up there, I've got to tilt it up in order to see that rocket, don't I? So where's the angle of elevation measured at? Yeah, but where is it? Is it this angle? Is it this angle? Is it this angle? Which angle is it?
The first one.
Which is which one? I can't remember. Between which two lines?
The red line and the green.
Okay, so we're going to say this is our angle of elevation. We're going to call that theta. Okay? And what are we asked to find? The rate of change of the angle of elevation. So we're asked to figure out what is d theta dt. Okay? When t equals 12, right? What is d theta dt when t equals 12? Now think about it. What do you expect to happen to that camera? I'm going to have to tilt it up. Am I going to tilt it up at the same rate all the time? Think about when a rocket takes off. What happens?
Is it photographic?
That's gonna go
Yeah.
up.
Think about when you've seen a rocket take off. What happens? It starts off kind of slow, doesn't it? And then the further up it goes, the faster it goes there, okay? So I'm not, when he first takes off, I don't expect to have to go like that. I'm just taking the picture. The further up he goes, the more I'm going to have to move the camera up, okay? So we don't expect this to be the same number all the time. Well, okay, we've got 2,000. We figured out that dx dt is 0. We're looking for d theta dt. When t is 12, tell me something else we know or don't know or need to know. S equals 55t squared, and we have not used that piece of information yet. Okay? We haven't used these two pieces of information yet. So what do we need to do there?
You can find out what S is.
We could find out S, okay? When t is 12, then S equals 55 times 12 squared, 55 times 144, right? Somebody with a calculating device, tell us what that is. 7920, okay? So let's just pretend that this is the rocket after 12 seconds. So what does that tell us then? That tells us, I need a different color. This distance is 7920, right? Y'all agree with that? All right. Well, talk to me then. We need to figure out some kind of equation that relates theta to this other mess that we got over here.
Oh, it's something with triangles.
It's something with triangles. Oh no.
That's the angle, something about the side of the angle spacing.
Mm-hmm.
So long ago.
That's almost it.
So long ago, Mr. Wood.
It's not so long ago. It's SOHCAHTOA.
But geometry.
Oh, okay. Oh, that. Okay. All right. I'm with you there. All right. So what?
Hypotenuse.
Yeah. So what is this?
Cosine, adjacent hypotenuse.
Uh-huh.
Tangent, opposite of the angle.
Tangent of theta is the opposite over the adjacent, isn't it? Okay. Do y'all remember that at all?
Yes, we read the story about the Indians.
Do you remember that, Miranda? Elaine, you with me? Gloria, you with me? Penny, you with me? Drew, you with me? All right, so tangent's opposite over adjacent here. So what can we say? At t equals 12, the tangent of theta equals the opposite. When t is 12, we said that distance was 7920, right? And the adjacent side is 2,000. It's 2,000 all the time, right?
Wait, which one's 2000?
The bottom one, yeah.
Okay.
Because the camera's 2,000 feet away, right?
I messed up.
Okay. Now, I need to back up because I kind of got ahead of myself here. I need to write it this way. The tangent of theta is the opposite side, which is h, over the adjacent side, which is x, right? Would y'all agree with that? Can you take the derivative of this mess right here? Tangent of theta equals h over x? You can. You don't want to, but you can.
Squared theta.
Sec squared theta d theta dt, don't forget him, equals h over x. How are we going to take the derivative of h over x? Low d high. Low d high minus high d low over the low squared, right? Isn't that ugly?
Yeah.
I thought so. Well, now, we got a bunch of letters. Do we have any numbers we can plug in anywhere? Do we have a number for x?
Yes, sir.
All right. So we've got a number for x. Let's put 2,000 in there. Do we have a number for dh dt? We don't know what it is yet, do we? I don't see anything written down anywhere. Do we have a number for h? Yeah, that's at 7920. Do we have a number for dx dt? Yes.
For dx/dt.
Yeah. We had this conversation while y'all were asleep and you were in the bathroom. What about dx dt? It's written in green on the board.
Equals 0.
Thank you.
Oh, it's the same thing that I said in the previous problem.
Why is dx dt 0? Let's go back to that since that's kind of pulling teeth there, it seems like. Why is dx dt 0?
Derivative
Because
is
the rock is
But why is the derivative 0?
it's not changing.
That distance isn't changing. The distance from the camera to where the rocket left is not changing, okay? Over 2,000 squared. That has to equal, we don't have anything for theta yet, do we? And we don't have a d theta dt. All right? Whew. Well, can we clean that up so it'll make us feel a little bit better? So we can say sec squared theta times d theta dt equals, this behind the minus sign is going to go away, and I'm going to cancel,
So it's dh/dt over 2000.
yep, so I'm going to make it dh dt over 2,000. What are we trying to find? What did we decide we were trying to find? The rate at which the angle of the elevation is changing. So we're looking for d theta dt. This is our goal, to figure out what that is.
We don't know what theta is.
We don't have a theta or a dh yet. Can we figure out what a theta or a dh are?
Wait, x equals 2000.
Weren't we almost there?
There's a way to figure this out.
Look right here. Let's come back up here and see if I can grab this piece right here.
Theta equals 79.
Yeah. All right, now I want to take that and copy it. All right, so now if we come down here, we've got this equation somewhere. That's an equation with one variable. Since we've had trig, we can figure out what the theta is. How do we do that on our calculating device? 7920 divided by 2,000 equals, second 10, second answer. It'll give you an angle there. I don't know what that angle is. Y'all are smarter than I am. Or your calculator smarter than I am, hopefully. 75? Wow. Somebody else, not that I don't trust Drew, but somebody else see if they can get 75 degrees out of that. Yeah, let's put it in radian mode. That'll be better. 1.32 radians. Does somebody else get that same thing? You did? All right. Okay, so we're pretty good. So now we can put 1.32 radians over here for secant and figure out what that is. We still need to know dH dt though, don't we? Well, where's H in our picture? This thing over here? This is H.
But the slope of that is
How did we come up with that 7920?
S equals 55 t squared.
We put in
So really, a better way to call, we could say that H is 55 t squared, right?
So the derivative of that is dH.
dH over dt equals 2 times 55 times dt over dt? Well, what on earth is that?
Time is changing 1 second per second.
What is dt dt, class? What is it? dt dt, what kind of number is that? 1.
Something over itself, so it's 1.
Something over itself, so it's 1. If you look at it algebraically, dt over dt says it's 1. Its time is changing at 1 second per 1 second. So what is dH dt then? 110. How about that? We can come back down here now and we can say we've got the secant squared of 1.32 times d theta over dt equals 110 over 2,000. And assuming we can punch our calculating device, we can figure out what that is. We don't have secant on our calculator, so we, bless you, so we probably want to say it's 1 over cosine squared times 1.32 d theta over dt equals 11 over 200. I hope everybody sees how I did that. It wasn't just poof magic. D theta over dt equals 11 over 200 times the cosine squared of 1.32. That was a hard problem. That's probably the hardest problem you'll see today. Okay? Do you see there's an awful lot of math to go through to get that? But you can actually go through and figure out. That tells you how fast that angle is going to be changing at that specific instant in time.
I don't think there's any way I could have gotten that just looking at it
Yeah.
on my own.
There shouldn't have been. But in a couple of weeks, you'll be able to.
I hope so.
By the test time. By the way, test is November 20th, the day before you get out for Thanksgiving. What better way to finish up? I mean, what better way to go off on your Thanksgiving break than with a test? I mean, wow. Okay. I don't want to dwell on that. You probably want to go back and look at this, and, to look at it later. The bright spot with this problem? You were sitting in class and watched me work through it instead of listening to this recording tonight saying, say what? What did he do?
I feel bad for not only calling
Yeah.
was.
And that's the last one for the day. So I was right. It's the hardest problem you're going to see today. Now, if you'll look at the assignment for tonight, there's probably only 6 or 7 problems because they're word problems like this, okay? So don't think you're going to run through them real quick because it may take 10 or 15 minutes to go through each one. Tomorrow, we're just going to do what? Go through, work some more problems. We're just going to continue to, not tomorrow, the next time we meet, whenever that is. Okay? So,
Yeah, you're working on it